All right, as Aisha just said, today I will be talking about imaging void spaces in lunar regolith using a joint ground penetrating radar and seismology approach. You may recognize me from yesterday. I'll put a plug in that I do have a poster from 5:30 to 7:30 on Kilbourne Hole, but for the next 10 minutes, I'll be focusing on a covered hole or a lava tube and subsurface void spaces. So on the left here, we have an image of Lava River Cave, which is in Arizona. My talk will be focusing a lot on terrestrial analogs, so I thought I'd put this in. This is what lava tubes look like. They are a type of subsurface void and very important for what Geodes, who has funded this project, is looking into. Other than Geodes, I would like to thank my co-authors who are listed here, as well as the UMD Seismology Group and Survey. So to go a bit into the motivation behind this project, Geodes is a NASA survey node that is looking into the geophysics of airless bodies, such as the moon, for exploration purposes. So looking at these geophysical bodies, we have multiple groups. I am a member of the lava tubes and voids theme, and we look at large-scale voids and microscopic scale voids, which are both important for determining landing site safety evaluation. How big are these voids? Where are they? How can we access them for using them as resources? Something that's important about this talk is that there's a lot of work that has been done on locating and imaging these subsurface void features using seismic or radar separately, but this is really the first joint radar and seismic effort. So shown here below, I have Skull Cave, which is another cave that we use as a terrestrial analog in Lava Beds National Monument. And it's very similar to lava tubes we expect and have some evidence to find on the moon, such as the Marias Hills Hole, which is a lunar skylight into a subsurface void that may be a lava tube. A little bit more on terrestrial analogs, which are really important. Why do we care about lava tubes on the moon? Why do we want to use them? We will use them for exploration and evaluation purposes, as they can be a resource, which is very important as they can be shelter for crewed or robotic missions. For those of you that were at the planetarium last night, you may remember during the movie, they had a section where there was a crewed housing structure that was kind of half buried beneath the regolith. And they stated that it's much more safe to be underground on the moon than it is to have structures on the surface. This is pretty analogous to if we use these subsurface voids that are already there, put our structures, put our crew in them, we will have shelter from cosmic radiation, weathering, and meteorite impacts. They can also serve as preservation sites as they will keep rock samples and possible evidence of life safe from these effects as well. We have terrestrial analog in situ data collection as a very important part of our work, where I have shown on the left here, this is an analog sort of seismic survey that we did at Kilbourne Hole this past April, where we set out 6 nodal seismometers following along what we would expect astronauts would do on the moon to collect seismic data over possible subsurface voids. There's also a lot of previous GPR work, such as the Ismaili et al. 2020 paper, which had modeled synthetically these portions of Valentine Cave, which is also in Lava Beds National Monument, and they put in parameters for Earth, Mars, and the Moon to look at how they could identify it and characterize it. Going more specifically into what I have done in my research, we have this lava tube model space shown on the bottom right. It's a semicircle 25-meter radius tube. It's filled with void to represent the moon, and the surrounding space is basaltic. So it creates this big density contrast that we can see in our models. For the simulation, we have 13 sources that are located along the surface above the tube. Number 13 is directly above the center, and then they're spaced 5 meters apart to the left to about 60 meters, so there are 13 sources total. Using symmetry, we can create the right-hand side of the model and get a full view of the simulation. So we use 2 different programs for the GPR and seismic, but they use the same model space and general process as we go through it. This joint seismic and GPR approach is here looking at the macroscopic voids, but we will also apply it to microscopic ones as well. Both of these methods, as I said, can determine how deep this tube is, how big it is, all of these parameters and details about it, but we are hoping to use them together to fill in gaps and get more precise details about them because of the density contrasts and difference between them. Seismic waves, they increase in velocity as you get denser material. GPR or electromagnetic waves decrease in velocity as you get denser material. I have shown on the bottom right what our seismic outputs can look like for different sources, where we have these hyperbolic move-outs that are very indicative of a reflector, the tube's ceiling. A little bit more on the details of our approach. What are the specific steps we take? We get these simulated seismic waveforms from SpecFem 2D. These are basically the raw data that we're looking at. We then perform the CMP stack, or common midpoint stack, where we take all 25 of our sources, line them up, stack them together to get a higher signal to noise ratio, which is shown in this middle image. And then both the GPR and the seismic approaches use the same 2D Kirchhoff method to migrate it and get the general structure. As you can see across them, we get this pretty similar depth of about 30 meters to the first reflector between the three, which is very accurate considering our original model was around 25 meters, so it's pretty close. We also have shown ground truth for the seismic of the PVP reflection and the SVS reflection, showing the outline of what this would be, and taking into mind that our models use the P-wave velocity in the Kirchhoff migration. We then take these and back check them against each other so we can make sure that our method is doing what we want by trading our data sets and using the opposite software on them, which I will go into on this slide. So from this individual workflow, we got that, okay, our CMP stacks and our migrations between the seismic and GPR, they have similar shapes shown here, the rounded top around 30 meters depth, and similar depth that I just said of 30 meters between the seismic on the left, GPR on the right. So in our back check, we essentially swapped our common midpoint stacks, and I ran the GPR in my seismic code, and John ran the seismic in his GPR code. And we got these shapes, which here, seismic's on the left column, GPR's on the right column. We still retain the general shape and the 30-meter depth to reflector between them. You can see there's this move out in the seismic, which retains even when it's put into a GPR code for both the P wave on top, the S wave on the bottom, and the seismic still resolves the tube ceiling and depth as separate reflectors between the GPR and the seismic codes. So we can conclude that our analysis of tube depth and general shape are viable via our geophysical method. So going a little bit more into broader implications, how can we further apply this? We have another subset of our team that is looking into a machine learning technique, which can create more regolith adjacent models, such as the one shown on the left here, where, okay, our codes have developed this large scale void space. They seem to be working for that. We've back-checked against each other. We have this benchmark that we can work with. And now we want to move towards smaller scale, more random scattering regolith media to create the layer that we would expect above a lava tube. So we're hoping to tie in these models that we have created using machine learning, where we have isotropic, anisotropic, small to large scale scatterers of varying vertical and horizontal sizes. And we hope to apply these models into the code that I've described to create more complex and realistic models. There's also something that I've been doing this past semester for classwork is autoencoder applicability. This is similar in theory to autoencoders, which have been used to detect anomalous heartbeats, electrocardiograms. And I'm thinking that similar in theory, you can use seismograms that have lava tubes, they're anomalous. You can try and use the same concepts to detect those. On to my summary slide, the takeaways that we've gotten from this. We found that the two programs we have used for GPR and seismic have built suitable lava tube benchmark models of the moon's shallow subsurface. Our analysis shows agreement between them, even in the back check for the migrated depth and general shape between the two. And we have taken some first steps in machine learning to simulate more regolith, detailed random scatterer models that we hope to apply our workflow to. I also have shown on the bottom here, we have some of the geodes team when we went out to Kilbourne Hole, but this past June, we collected in situ data at Lava Beds National Monument over Skull Cave, which we're hoping to apply our models to get some real world in situ data analysis using our codes, and of course, go on to more complex simulations. Thank you for listening.